and so you're doing this quiz during Bearcat time, right? Tomorrow, Will?
Yeah.
That's your plan. All right, so anyway, on to limits. So yesterday, or Friday, I guess, I should say, we talked about, we had this up on the board, so I don't need to rewrite this. This is the same thing we had up here. So we had two different types of limits. We got limits as x approaches a number, as x approaches 2, as x approaches 3. Two-sided limits. That's where you're talking about the cars meeting at 2 or at 3. Okay? But you could do from the left or you could do from the right, on a limit like that. Then we also introduced this idea of x goes to infinity. Now that's a horizontal asymptote situation. What's happening to the graph? The y values way out here, right? And limits are all about the y values, the outputs, right? What are the outputs doing? What are they approaching? And again, that's what you want to ask yourself. What are they getting close to? What are they approaching? That's what it's about. That's the answer. So what's the graph doing as x goes out to infinity or negative infinity? Okay, and so of course you can't have two cars. You can't have the cars meeting in that situation. Just one car. It's on its way out to infinity or negative infinity. What y value is it going towards, or is it going towards 1 at all? It might just be going to infinity, right? Just like x squared. X squared just going up to infinity. So the limit doesn't exist. Okay. And we said if x is approaching a number, you can just plug it in and get a number. You might get 0, 0. You have to do some algebra. We're going to add a new piece to that. I left a little space here actually. We're going to add a new space to that today. And then of course you could get a number divided by 0, and that's going to be your vertical asymptote situation. And that's when infinity usually gets involved there as well. So the blue is kind of the new stuff we added with infinity. Because whenever you get a vertical asymptote, you're going to have infinity going on. Okay? Heading up there towards 0. Okay? Zach, I need to see homework from last couple of days too. 4.1, yeah, and the worksheets. Okay. All right, so I want to start off here, before we go over the homework problems, I want to start off with some examples of does not exist. Okay, what are some of the different scenarios you're going to run into where you're going to get does not exist? Okay, so the first situation, of course, that we learned about was this, scenario right here. You get a graph where that's happening like that. The cars don't meet. Okay, the limit doesn't exist. Okay, so maybe we could even, that's the first one we learned about. The cars don't meet.
How do you describe that?
Well,
we were working on 3 things that
No. Okay, see, so let's don't confuse those. The 3 things we talked about were continuous functions. This is discontinuous because the limit doesn't exist. Right now we're talking about why doesn't the limit exist? It's because the cars don't meet, right? We had 3 different examples of discontinuity. That's different than the limit not existing, right? No. Well, that could be. That's... Anytime we've learned something, that could come up again later, right? You need to know that. So I'm not going to say it's not going to be on there. There might not be a question about the continuous function or something. It's not a big emphasis of what it's supposed to be, right? It's kind of like that, this is going to have derivatives on it, right? We're going to have to be able to do a derivative, whatever. Always, right? We're done with chapter 3, the gateway test, do derivatives. So yeah, even though I don't say that, it's on. You know what I mean? Does that make sense? So, but that's where we were talking about stuff like that. See, so like that right there is discontinuous, right? That function is discontinuous. You have to lift your pencil. But does the limit exist there? The limit exists, right? The cars meet, right? So it's two different ideas, 2 different questions. And then the same thing here is we said, well, this is also discontinuous, but the limit exists. It's just that the limit is different than the y value, than the output. So those are different questions. Okay? So the cars don't meet, right? Now, what's another example of the cars don't meet? Well, you could have this, right? You could have that situation with the vertical asymptote. There, clearly, the limit does not exist. Now, you would have to talk about, but you would have to remember, when you give this answer, you've got to give more than that. So you say does not exist, and in this say you'd say, okay, as x approaches I don't know, let's say this is 2. As x approaches 2 from the left, let's say this is a y value of 4 and this is a y value of 6 maybe up here. So x approaches 2 from the left, you're getting 4. As x approaches 2 from the right, you're getting 6, that kind of thing. All right. Oh, hang on here a minute. I just realized something. I added something. Bear with me a second. Okay. All right, now. All right, so this is the part we said we added now today. So you would have to give all of that as your answer. On this one, you would say does not exist, right? And let's say this is an x equals 2 again. And then you would say x approaches 2 from the left would equal infinity, and x approaches 2 from the right would equal negative infinity, right? Like that. And right, whenever you've got one of these limits where it is not equaling a number, it's got to be does not exist. The left-hand limit then might have a number, and the left-hand limit, it's okay to say equals infinity here when it's a left or a right-hand limit. Okay, that kind of thing. So if I just would have asked on this question, what's the limit as x approaches 2 from the left, it would be, you could throw in does not exist. If I just asked for the limit on the left, probably the best would say does not exist, goes to infinity, right? Same kind of thing. Now, what are some other examples? Well, plain old parabola, right? The limit as x approaches infinity. Well, we would want to say does not exist, and then we would say infinity, right? Because as x goes to infinity, this thing is just going up, 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 like that. Or e to the x, or something like that, right? Here's another interesting. The limit as x approaches infinity of sine x. What would you say there? Oh. No, I'm not talking about that one that goes smaller and smaller and smaller. I'm talking about regular old sine x. Way out here to the right, what are the y values approaching? Well, the y values are between 1 and negative 1. But that's not the question. The question is where they approach. I know what you guys are thinking of. You're thinking of the one I said yesterday or Friday where I had sine x over x squared or something like that. Okay, then I said, okay, the top is going between negative 1 and 1, but the bottom's getting bigger and bigger and bigger. So the fraction is negative 1 over 1 divided by a bigger and bigger and bigger number, which is getting smaller and smaller and smaller. So the fraction is heading towards 0. So we said the answer was 0. That's a different question. What are these y values approaching, getting closer and closer and closer to as x goes way out here? Does not exist, right? It doesn't exist because there is no value that they are approaching. They are not approaching a value, right? The y values here are not approaching a number. They're bouncing back and forth between negative 1 and 1. So it does not exist, okay? And then and we said it's not enough really to just say does not exist, right? You got to explain what's happening. So I would write it out in words, but basically you would write out that the y values are not approaching any number. They are just bouncing back and forth between negative. They're taking on values between -1 and 1 forever. So there would need to be some sort of explanation on that. So it's really not enough. I mean, for the most part, on any problem, it's really not enough to just say does not exist. You've got to then kind of explain why. Now, the usual reason is, well, because the cars don't meet. So you look on the left and the right. If you're doing an infinity problem, the reason it does not exist, right? If its x goes to infinity, because it's just going to infinity or negative infinity. But it could be, I'm not going to write that over there because I'm not going to write that in here, but it's just kind of a special case, doesn't have very much. But sine would be one where the limit doesn't exist just because it doesn't approach a number. It just goes, it bounces back and forth between -1 and 1. Okay? All right. So those are some examples of does not exist. Okay, I had this up on the board right at the end on Friday, and so I want to go over this again, and then this is going to help us, I think, as we get into the homework, maybe just help understand a few of the problems maybe a little better. But remember, we said infinity is not a number. Infinity is not a number. We can kind of treat it like a number and think of it like a number and use it like a number, but keep in mind what we're really meaning when we see infinity is larger and larger numbers, right? We're just talking about approaching. We're just talking about something that's getting bigger and bigger and bigger, increasing without bound. Okay. So when we talk about 1 divided by infinity, we're not really dividing by infinity. We're saying, what is this fraction approaching? What value is this? What are these values doing on this fraction as the bottom gets bigger and bigger and bigger? That's what's going on. We can just write 1 over infinity, but what we really mean 1 divided by bigger and bigger and bigger numbers is getting what? Closer and closer to 0. So we'll go ahead and say equals 0, but that's not really, technically that's not right. Technically what we mean is the limit as x goes to infinity of 1 over x equals 0. That's what technically that means. Okay, but we use it kind of as shorthand, and I think it's a good way to remember. As a matter of fact, I don't know if you noticed on the video of the calculator, but I had up on the board, I had k over infinity equals 0, and k over 0 equals infinity. Now, plus minus. Okay, I had that up on the board. Because basically that's just a fact that is saying, that's just saying that a number divided by a really big number is getting really small. And a number divided by a really small number is getting really big. That's all that's mean. Okay? So when you see something over infinity, think 0. When you see something over 0, think, now I say something, I don't mean 0. We can't, this is different than 0 over 0 or infinity over infinity. We're going to talk about that a lot today. Okay, I'm talking about a number, 7 over 0. 7 over infinity. That kind of thing. A k, a constant. Okay? But we just kind of think of them as opposites. Right? Some people even would say the reciprocal of 0 is infinity. And the reciprocal of infinity is 0. You get what I'm saying? Right? Like the reciprocal of 2 is a half. The reciprocal of 100 is 1/100. The reciprocal of 1,000,000 is 1/1,000,000. You see what I mean? As you get bigger and bigger, it gets smaller and smaller. So it's like 0 and infinity. We can almost think of them as reciprocals. Okay? In a sense. Okay? So like here, we got 1 over infinity equals 0. Likewise, I could say this. That's why it does not exist. That's why it's undefined, right? I think I said this earlier. What I always tell my freshman or my sophomore Algebra 1B kids, I say, why can't you divide by 0? Because you're not really dividing by 0. You're doing 1 divided by a really small number. That's a really big number. Well, if you do 1 divided by 0, you're doing 1 divided by the smallest number. So you should get the biggest number. There is no biggest number, right? So that's why you can't divide by 0. But we could just say that, right? So it's like the reciprocals, okay? All right. 3 times infinity is just infinity. So in other words, that's where we get into different sizes of infinity, right? That's the infinity hotel thing. You know, you got the thing is full, and all of a sudden you move everybody to an even room, and you got all the odd rooms open, right? So all of a sudden it seems like you got half as many people there, but not really. Half times infinity is still infinity. Okay, now where it really will start to get interesting, and we're going to deal with this today, is what happens when you got 0 times infinity. Now, I think I said this here today. It feels like it should be what? Feels like it should be 0, right? I mean, just the 0 times. But that's 0 times a number, 0 times infinity. Well, what this really is something getting small times something getting big. Now, it depends. Now, I didn't get a chance to go through this, but let's look at it. So if x is getting really big, what's this one doing? And then this one, of course, is getting really big, right? 0 times infinity, right? Well, what's 1 over x times x? So the answer to this actually is 1. Now, if I would have made this 2 over x, then the answer to this would have been 2. So you see how I could have made this come out any number I want. It's 0 times infinity, okay? Now, what about this one? As x gets really big, what's this doing? 0. But what's this? That's 1 over x, and as x gets really big, that's just going towards, look at that. So that time we got 0, okay? How about this one? As x gets really big, this is going towards 0. This one's going towards infinity, but what's 1 over x times x squared? X. And as x gets really big, that's going to infinity, right? So do you see how 0 times infinity could be 0, it could be infinity, or it could be any number in between, right? I mean, and we're going to have a name for that. That's called indeterminate. We're going to write that down later. That's indeterminate. We don't know, and then that's where I said this is where calculus is going to get involved, right? It's about the rates. This is going towards 0, this is going towards infinity, but it depends which one's going there faster. This one, they balance out. 2 over x is getting small at the same rate that this one is getting big. And so they kind of counterbalance each other, and they end up at 2. This one, which one of these is getting small or big faster? The x squared, right? The x squared. So this is getting small faster than this is getting big. X squared is changing faster than x is changing. Okay? So the 0 is overpowering the infinity, and this one goes to 0. And then likewise here, other way around, the x squared is overpowering this. So this one's getting big faster than that's getting small, so the infinity grows. So it's kind of a race, right? And the rates are involved. That's how the derivatives get involved. But the bottom line is just understand 0 times infinity does not mean 0. It could be anything. Okay? And the same thing is true with 0 divided by 0. And infinity over infinity. You want to say 1, but that's not true. We already found out here that 0 over 0, we keep going. There could be an answer. It depends on whether the top's getting small, bigger, faster than the bottom's getting small. And same thing is true here. You got top and bottom both getting big. It depends on which one's getting bigger faster. So you could get anything here. You could get 0, you could get infinity, you could get any number in between. Just like this one. Okay? All right, that's where we're headed with this. All right, let's go over the homework. Some of these hopefully were really easy, and then a few of them probably made you think a little bit. What'd you get on this one? 0, right? So some of these on the homework, you're not going to have a lot of work to show. There's some of them you'll have more. But some of them you just kind of reason your way through. That's going to be 0. Okay, number 10. Also 0. Now the square root shouldn't really throw you off. You just got x getting really, really big. When you do the square root of a really big number, it's still really big. Not as big, but still really big, right? If you're getting in the billions and you do the square root, now you're just in the 100,000s, still really big, right? I mean, as you get bigger, bigger, bigger. Okay, the square root of a googol, is still really, really big. It's not as big, but it's still really, really big compared to the 5, so it's headed towards 0. Okay, what about this one? -1/2. And this is one we said, now we're going to introduce another way to do this one, but basically, and the key, of course, is t's getting big. Okay, if this said t is approaching 2, we treated this totally different. But t's approaching infinity, so the top's getting really big. So basically, we have infinity over infinity. That's going to be negative infinity, but it doesn't matter. So this is really an infinity over infinity situation because the top's got T in it, the bottom's got T in it. They're both getting really big as T gets bigger and bigger. But the difference is, as they get really big, what I like to think of is that the 3 doesn't matter. So this essentially becomes 2T, and here the 5 doesn't matter, and this becomes that. The T's cancel, right? And we get that. On the video, they said you just take the coefficient in front of the highest power, right? Take the coefficient in front of the highest power, so the 2 and the -4, you get -1. Okay? Now that's a horizontal asymptote. What that means is that graph is approaching, so if we graph that, we go way out here to infinity, that graph is coming down towards -1/2, or maybe it's coming up from underneath and it's approaching the line y equals -1/2, right? So understand what this means. Same thing with this one. Same thing with this one. This means that way out here at infinity, it's coming down and approaching 0. I don't know if it's above or below. Maybe it's down here. It's a horizontal. Understand that, right? Make sure you understand that when you find x approaching infinity, you're finding a horizontal asymptote. Okay? Way out here. All right, so that one's approaching -1/2. Okay, but then they shift gears on you, right? Same problem, except they do that. So what do? You just plug a 0 in. What do you get? You get 3/5. 3/5. So don't, understand, we talk about infinity, we talk about high powers dominate, we talk about stuff like that. Yeah, that's when T's getting really, really big. You think about those kind of things. But here we're talking about T getting towards 0. Well, that means this is just going to go to 0, this is going to go to 0, and you're going to be left with the 3/5. Okay? So it's interesting, when T was getting really big, the 3 and the 5 didn't matter. When T's getting really small, the ones with the T's don't matter, because they're going to disappear. They're essentially going to nothing. Okay? What about this one? What do you have to put for your answer on this one? Does not exist. Infinity. Gotta have it. Gotta have the does not exist. Okay? Now, why is that? Well, because as x gets really, really big, the +1 doesn't really matter. And this just becomes x squared over x, which is equal to x. So as x gets really big, this is going to infinity. So the limit does not exist, because it has to be a number. If the limit exists, it goes to a number. It doesn't approach a number, it approaches infinity. Now, if you I don't need to see this work right here. I don't need to see this work, right? You can just look at that and say, hey, the top's got a square in it. It's getting big a lot faster than the bottom is getting big. So this is just going to infinity, and, and that'd be fine. All right, now what if this would have been negative infinity? X approaches negative infinity. Because the top will still be positive, right? Now sometimes if x approaches negative infinity, you get negative on top and bottom, and they just cancel each other out. It's still positive infinity. But in this case, you go to negative infinity, the top is squared, so that'll be positive infinity. And then negative here, but then this is going way faster, so then it would be negative infinity. Does not exist, it'd be negative infinity. Okay? But if you want to do this work, the 1 really doesn't matter. It looks like this. You cancel, you can do that. But you could just say, hey, the top's got a higher power. It's just getting bigger a lot faster, kind of like the video said. Okay? All right. What about this one? 1/2. Again, the 1 doesn't really matter. The 3 doesn't really matter. This is x squared over 2x squared. X squareds cancel. 1/2. Okay? Again, that's a horizontal asymptote. If you were to graph that function. Okay, 15. What do you got here? That's the one we talked about. That's the one we talked about yesterday. X gets bigger and bigger and bigger. This is just bouncing back and forth between -1 and 1. So the bottom is way over powering the top, and it's going towards 0. Okay, 16. Does not exist, and then what? Negative infinity. Okay, oops. Headed towards negative infinity. Now, what's going on? As the top is going towards getting bigger and bigger and bigger, but negative, and when you cube it, it'll stay negative, so the top's getting really big, and this is bouncing back and forth from -1 to, now remember, negative infinity, so we're going way out here on the cosine graph. On the cosine graph, way out here to the left, it's going back and forth, -1 to 1, so if you do 2 plus that, that'd be 1 to 3, so the bottom is just bouncing back and forth between 1 and 3, right? Or you could think of 2 plus cosine as a graph of its own, right? It's just gonna shift up 2. So it's going to be up here. So it's always going to be positive. So you're just going to get these positive values between 1 and 3. But on top, you're getting bigger and bigger negatives divided by 1 to 3 somewhere. So it's just getting bigger and bigger and bigger. Okay? And towards negative. So negative. Okay, good. 17. Why? Because that's what the back of the book said. Why? This is a fundamental understanding of these types of functions that they are going to ask you about. You will see this in a variety of ways on the AP test, in the semester final or the midterm and that kind of stuff. They want you to understand that any kind of an exponential, now I'm talking where a is greater than 1 now, right? 2 to the x, 3 to the x, 4 to the x, something like that, is going to grow way faster than any power function. Even if you had x to the billion, right? Even if you had x to the 1 billionth, 2 to the x will eventually get way bigger. X to the billionth in the early stages will be bigger than 2 to the x. But eventually, somewhere down the line, the power function will outgrow and grow faster. Okay? So understand that the top is going to go faster than the bottom, no matter what this power is here. Okay? So even if some people think, well, if that would have been x to the third, would that be? No. Eventually, an exponential function will always outgrow a power function. Okay? So this is going to go to infinity, and that's exactly right. You just say the top is getting bigger faster than the bottom. And then, of course, what happens when you put a negative infinity on it? Now, 2 to the negative x, that's like 1 over 2 to the x, right? So now, all of a sudden, the bottom's going towards 0. And then this is getting really big. Well, that's definitely going towards 0. So you got the top getting small and the bottom getting big. Both of those things cause a fraction to get small. So that's going towards 0. Okay? All right. This was a tough one. This one would be, well, I shouldn't say that tough. It's kind of the same idea. What did the bat say? What'd you have?
0.
Why?
Because e is obvious, e to what number 2.
Right.
And x to the 2 is just going to get bigger a lot faster.
Yeah, yes. Now, to be honest, so it doesn't get big a lot faster. Let me show you what these two graphs look like. This is well, of course, you guys should know this one, right? Now, we just got done saying that exponentials get big fast. Well, the log is the inverse of that, right? The log is the inverse of e to the x. So this gets big very, very slowly. E to the x gets really, really steep, almost vertical. This gets almost horizontal, right? Now, x to the 2/3 actually looks like this. If you graphed x to the 2/3, looks like this. Now, the reason it looks like that is because the 2 up there is like squared, so it makes it positive. X to the 1/3, the cube root graph looks like this. It comes in here. You guys probably would understand that. That's the inverse of the x cubed graph, right? That's x to the 1/3. But when you square that, it makes this bottom become positive and then a little steeper, but because it's squared. But so it basically becomes this. So the idea is which one of those is getting big fast? Well, it's hard to tell, but it's basically this inverse relationship, like you said. Since an exponential gets big a lot faster than a power, when you have the root, like a 1/3 or 2/3 or something like that, when you have a root, those actually get big faster than the logs, right? Because it's that inverse relationship, okay? So since the exponentials get big faster, when you do their inverse, they get big slower. Okay, so the bottom actually is going to get big faster here. But see, this is where this new rule we're going to learn is going to come in. This would be a great one for that one to do. Because you would look at that and you might not know that relationship, and that might be a little tricky one. But it is 0. Okay, what about this one? This is 0 also. Because how do you do this? Well, this is where it's okay to think about plugging in an infinity. So what's pi over infinity? That's 0, but again, technically that what we're saying is as x gets really big, this fraction in here is getting really small, going towards 0. And so you have sine of something getting close to 0. Well, here's the sine graph. As x gets close to 0, what are the cars doing? They're meeting right there at 0. So, 0. Okay? So that's just a little different variation off of that. And then this last one, again, we can just plug in a 0, sine of 0, 0, sine of 0, 0. Just kind of, just plug in. Okay, so we had a little bit of variety there on some different problems where we're plugging things in and we're thinking about infinity, we're thinking about powers and what grows faster and that kind of thing. Okay, the last one you had then was this. Okay, it wasn't, was this the one we had? Okay, so the first thing, of course, you do is plug in a 3, and you get what? 14 over 0. Okay, so as soon as you get, and I threw this in here because the book didn't have any of these. Now, it's going to have some, I think, in our next set of assignment, our assignment for tomorrow. But I threw this in here because we had talked about this right here, right? We talked about this, but we didn't really get any of those in the homework. So I wanted to make sure you did one of those. So if you get a number over 0, you know that's a vertical asymptote. It's this situation here. Okay? It's this situation here. So we got to look on both sides of that. All right. Oops. So we get 14 over 0. So we have to say, okay, so we right away we write down does not exist. Right? And then we're going to do 3 on the left, which is 2.999. And we're going to do 3 on the right, which is 3.001. Okay, 2.999.
Small positive.
Small negative. And up here, basically 14. 13.999, right? You get something a little less than 9, plus 4, plus 5. So basically 14. And so that's negative infinity, 3.0. So this would basically be 14. Again, roughly 14 over a 3.01 minus 3 is a really small positive. So 14 divided by a small positive would be 50. So that, I want to see all that. All that. Okay, so definitely going to have some of those.
Your infinity looks like Alabama's A.
This,
Yeah.
that, actually, oh gosh. Actually, you're really good, Alabama A. That, I could never draw that A. That A. Sometimes I do that. I don't know. Sometimes if I take my time, I can do a good infinity. And then sometimes I get this thing going on. I don't know. All right. So let's, in your notes, on your homework, whatever, let's do these two problems real quick right here. Since I don't know, who knows when you did this homework. Most of you just last night, Sunday night, so maybe you're fine with it. Maybe it hasn't been that long. But those two problems right there. right, what'd you get for the first one? 1/4. First thing you do is plug in a 2, and you get, okay, so that means keep going. So on this one, what'd you do? Factor out the bottom. Okay, x plus 2, x minus 2. Right, that's the easiest of the algebra things we had, which is this. And you plug your 2 back in, you get 1/4, right? So there's no infinity, no thinking about high powers. That doesn't matter because we're doing x approaches 2. So we get this. Okay, on this one, now, I know you wouldn't have wrote this, but this is an infinity over infinity, right? The top's getting big, the bottom's getting big. It's that kind of situation. But you would also notice, so what'd you get for the answer on this one? 3/4, right? Because this is where we said, okay, the -7 doesn't really matter, so it's 3x squared. On this one, neither one of those two really matter, so it's just 4x squared, because if you have 4 billion minus a million, or whatever that would be, right? But whatever. It's unimportant, right? What we talked about on Friday. So it just becomes this, which essentially reduces to this, or like they said in the video, just take the highest power, take the coefficient of the highest power, because that's all that really matters. And that is your answer. And that would be a horizontal asymptote. Horizontal asymptote. This would actually be a hole in the graph. Typically 0 over 0 is a hole in the graph. So what we're saying is the cars are meeting at 1/4, right? This though is a horizontal asymptote because we're saying as x approaches infinity, right? So we're talking about way, 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 way out there, okay? So understand all these connections. All right, so what we want to focus on today then is this scenario here. What is going on here? Is there a way we can do this? Well, we've hinted at it already. The bottom and top are both getting small. They're both, when x is approaching 2, the top is getting really small, the bottom is getting really small. But the question is, what's getting small faster? At what rate are they getting small? And then the same thing is true here. Top's getting big, bottom's getting big, but at what rate are they getting big? Well, of course, that's the derivative. That's the derivative. So, we've got this thing called L'Hopital's rule. Okay. All right. So, I'm not going to write in all of the stuff that's in L'Hopital's rule. They call it Theorem 3 here in the book. So, if any of your homework says use Theorem 3, they're talking about L'Hopital's rule. Okay? It says let f and g be differentiable functions. Okay, so the idea here is that if the limit as x approaches a of f of x over g of x goes to 0 over 0 or infinity over infinity. Now, when we say infinity over infinity, it could be plus or minus, doesn't matter. Okay? And also, if the limit as x approaches infinity, and again, that could be plus or minus, of f of x over g of x, goes towards 0 over 0 or infinity over infinity. Then, the limit of f of x over g of x is equal to the limit, and I'm not even going to put, well, okay, I could say x approaches a, or it could be x approaches infinity, either one, is equal to the limit of f prime over g prime. In other words, what this is saying is if you have a problem that is 0 over 0, so it's got to be a fraction, right? So that's why it's f of x over g of x, right? It's got to be a fraction. To come out 0 over 0 or infinity over infinity. If you get one of those two situations, then you can just do the derivative of the top and do the derivative of the bottom. Now that should bother you a little bit in the sense that, wait a minute, we have the quotient rule. Remember, u prime v minus uv prime over v squared. I always worry a little bit that people still doing the gateway test are going to work these problems, and they're going to get so used to doing the derivative of the top and derivative of the bottom that they'll forget, we're not doing the derivative of the fraction. That's not what we're doing, right? We're not doing the derivative of this fractional function. What we're doing is applying L'Hopital's rule, which tells us that to get this limit, we need to see how fast the top and bottom are changing. So what we do is do the derivative of the top, that tells us the rate of change of the top, and we do the derivative of the bottom, that gives us the rate of change of the bottom, and then we compare those. So it's a completely different scenario, right? So in this case, it is okay to just take the derivative of the top, the derivative of the bottom, and then do the limit of that. Now, it turns out that if you get 0 over 0, infinity over infinity of that, then you do it again. You can do the derivative again of the top and the bottom until you eventually either get an answer or can tell that you're not going to get an answer, or it's going to be does not exist or whatever. Okay? So, let's go back and look at that on these two problems here. So right here, as soon as I saw that I had 0 over 0, now understand, L'Hopital's rule does not work if you don't have the hypothesis part, the if part, okay? If you don't have that, then this doesn't work. So you don't do it. So if we go back into our homework, right, would L'Hopital's rule work here? No, it's 3 over infinity. Here, no. Now this was infinity over infinity, right? So we could have done L'Hopital's rule, okay? Well, let's just do it on this one. So what's the derivative of the top? 2. What's the derivative of the bottom? Okay, easy that one, right? Negative 1/2. Okay, how about this one? As t approaches 0. Do L'Hopital's rule on this one? We don't have 0, 0. We just plugged in a 0. We got our answer, right? So L'Hopital's rule doesn't work. What about this one? Infinity over infinity. Aha. Yes, this is an infinity over infinity. Now, it'd be negative. The bottom would be negative infinity. It doesn't matter. So L'Hopital's rule would work. So what's the derivative of the top? Derivative of the bottom? 1. Now, as x goes to infinity, it's infinity, right? Do the derivative of the top, 2x. Derivative of the bottom is 1. As x goes to infinity, that goes to infinity. So you say does not exist infinity. See that? See what I mean? Now, I don't know that L'Hopital's rule any easier. I think what we did was pretty easy, right? We just said high power dominate, high power is getting bigger faster, it's going to infinity. So I'm not saying you have to use L'Hopital's rule. It's a tool. It's just one tool in the toolbox. All the stuff we did Friday and all the stuff we've done so far today is all good. It's all fine stuff to use, right? And you can do it. You don't have to use L'Hopital's rule. Okay, now I think on the homework it might say, no, it doesn't. Well, there's a couple of them where it says use L'Hopital's rule. It's probably a hint that, hey, L'Hopital's rule works. But it's just a tool. Now, I'm not going to say on the quiz you have to use L'Hopital's rule. I won't even mention L'Hopital's rule on the quiz. I'm just saying evaluate the limit. It's just one tool you have to do the limit, and it works when you have 0 over 0, infinity over infinity. Okay, on this one we got infinity over infinity. So, right? So, derivative of the top, 2x. Derivative of the bottom. Now, you got a choice here. At this point, you can just cancel and get 1/2. Or you can say, hey, that's still infinity over infinity. So I can do it again. Derivative of the top, 1/2, right? But you can just cancel the x's. All right. What about this one? Was this infinity over infinity? No, this was negative 1 to 1 over infinity, right? So that wouldn't work. This one wasn't infinity over infinity, so L'Hopital's rule wouldn't work. This one was. Now, here's where this could come in handy. This one was infinity over infinity. So what's the derivative of 2 to the x? Times ln2 over the derivative of x squared. Now at this point you could say, hey, that top is going to get way bigger, but let's say you didn't. So this is still infinity over infinity. So do the derivative again. What's the derivative? 2 to the x times ln 2. 2 to the x, ln 2 times ln 2. Because ln 2 is just a number. ln 2 is just hanging out there. Hangs out. You derivative 2 to the x is 2 to the x ln 2. You got another ln 2. What's the bottom? Derivative 2x is 2. So clearly the top is still getting big because of that, and the bottom is just 2. So this is definitely going to infinity. So now we can see for sure that that's what would be going on using L'Hopital's rule. Okay, 18 was another infinity over infinity, except it was negative infinity, right? So you'd say, okay, oh no, this wasn't, right? This was 0 over infinity, wasn't it? This was 0 over infinity, so we don't use L'Hopital's rule for that. Okay, this was infinity over infinity, but they were slow. So this would work pretty good. Derivative of the top, 1 over x. Derivative of the bottom would be 2/3 x to the what? Negative 1/3, right? Here's where L'Hopital's rule would have been a really handy one to use. Because look what I can do with this now, algebra-wise. I can just make that negative 1, and I can make that negative 2/3. Or no, that's negative 1/3, excuse me. And then I still got this 2/3 down here, which would actually flip up as a 3 halves and be easier. Now I can just subtract those powers. What's negative 1 subtract negative 1/3? Negative 2/3. So this would be 3 halves x to the negative 2/3. Now what happens to that as x gets big? Doesn't that get small? Right? Because it's x to the negative power, so that'd be 1 over x to the 2/3. So this would be getting really small. See? So that's where, this is one where L'Hopital's rule could have really come in handy, because we really didn't have a good idea of which one of those was growing faster. I mean, we talked about how you could reason your way through it, but L'Hopital's rule just does it for you. Now, some of you might not like those fractions and stuff you got to deal with, but that's just algebra, so we should be able to do that. But okay, so that would work. This one wasn't 1, and this one wasn't 1. So L'Hopital's rule. So here's 2 more. So we got 0 over 0. So we can do the derivative of the top is 1. Derivative of the bottom is 2x. Did I do that right? Now plug in your 2. What do you get? 1/4. See how slick that was? No factoring needed. Really be nice on those conjugate ones and stuff like that, even though you got square roots and stuff. But if you didn't like doing the conjugate or the bow tie, this would be a pretty good way to go. Here you got infinity over infinity. Do the derivative, you get 6x. You get 8x minus 1. That's still infinity over infinity. So you do the derivative again, you get 6 over 8, 3/4. Right? So L'Hopital's rule just says, if you get 0 over 0 or infinity over infinity, and that's a must-have, then you got this. Okay, so indeterminate forms. So our indeterminate forms are 0 over 0, infinity over infinity. Now what that means, indeterminate means we can't determine if there's a limit. We got to do more. That's why I always said keep going. Keep going. Well, now we've added to our list of keep going. We can do L'Hopital's rule. Now there's one more indeterminate form we got to throw up there. 0 times infinity. Now here's the problem. You can't use L'Hopital's rule on 0 times infinity. It's got to be 0 over 0 or infinity over infinity. Right? We can do L'Hopital on those two. But we can't do L'Hopital on 0 times infinity. Well, guess what? Remember what I said about reciprocal? Remember that? Well, 0 times infinity, I can either write as 0 times 1 over 0, because isn't 1 over 0 basically infinity? Remember that? We said that? 1 over a really small number is a really big number. Or I could do the reverse of that. I could do 1 over infinity times infinity. 1 over infinity is essentially 0. So both of those would end up, they would end up being either 0 over 0 or infinity over infinity. Does that make sense? Okay, so when we have a situation where one's getting small and the other's getting big, and we want to tell which is getting big faster, we can do the reciprocal and turn it into a fraction, and then we get something we can do L'Hopital on. Okay, so let's do an example. Let's do a couple of quick examples of that. So right here's a good one. Okay, as x goes to infinity, now what's x doing? X is getting big, and what's e to the negative x? So that's small. So what I want to do is do the reciprocal of one of those and divide it. Well, what would be the easy one to do reciprocal? The negative, no. Well, 1 over x would, but that would be e to the negative x. Isn't that the same as 1 over e to the x? Right? So the easy one to me would be to do this, which is just x over e to the x. Isn't that the same thing? Now look what you got. You now have infinity over infinity. You see what I mean? So the idea is you just rewrite one of them. So just do that. And so now do your L'Hopital's rule. Derivative of the top, 1. Derivative of the bottom, e to the x. So the answer on this is 0. Now, again, would you have to do L'Hopital's rule? No. You could look at this and you could just say, which one of these is getting big faster? The bottom's getting big, way faster. Or you could even look at this and say, e to the negative x is getting small, but it's an exponential. So it's getting small way faster than this one's getting big. So even then, you could have said, hey, 0 is going to win this race. 0 is going to win the race over the x getting big. So you could have done it that way anyway. But the point is, if we want to use L'Hopital's rule, it's got to be 0 over 0 or infinity over infinity. So we might have to rewrite it, and then we can do L'Hopital's rule. Derivative of the top, derivative of the bottom. Okay? Here's another one. X approaches 0 from the right. Now here's natural log. Here's a natural log graph. That's why we're doing 0 from the right on this one. So what is x squared? X squared is going towards 0. What is ln x? As you do 0 from the right. No. The car approaching 0 from the right, negative infinity. So we have a negative infinity situation here. Now, you could flip that x squared down and make it a negative 2 power. Okay, we can do that. So this would be ln x over x to the negative 2. Would you agree with that? Now what do we have? Now we have negative infinity over, and then what's this as x gets close to 0? 1 over x squared, right? As x gets close to 0, that'd be going towards infinity. 1 over a really small number, right? We'd have 1 over 0, which is basically infinity, right? So we've now turned it into infinity over infinity. So we can do L'Hopital's rule. So L'Hopital's rule would say the top is 1 over x, and the bottom is negative 2x to the negative 3. Now that's like this one we had a little bit ago where you can subtract power. So let's rewrite the top. Top's x to the negative 1. This is negative 2x to the negative 3. So let's subtract those powers. Negative 1 subtract negative 3 is 2. So we end up with an x squared on top, basically, and a negative 2 on the bottom. Now what's that doing as x goes to 0? As x goes to 0, this is 0. 0 over negative 2, right? So I just did L'Hopital, so I just flipped that down. So I had a 0 times infinity situation. So I just flipped that down, made it as the infinity over infinity. Because remember, reciprocal of 0 is infinity, basically. Okay? And then I just did the derivative of the top, derivative of the bottom. Remember, we're not doing quotient rule. We're not doing the derivative of this function. That's not what we're doing. We're checking the rate that this is changing and the rate that this is changing. So we do the derivative of the top, derivative of the bottom, rearrange it a little bit here, and we get 0. And again, you might have known that. You said, hey, ln x is going fast, 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 fast here. Right? X squared, that's heading towards 0 here. Okay, but this is slower. This isn't like an exponential. It's like the opposite. So it's not like what an exponential does. Okay? So that is not going to, this is going to outweigh it. Okay, so the 0 takes precedence. All right, so your homework is going to be the 4.2 day 2 problems. And then I would add, I guess I would add then to, in our notes from the other day, I can add in here, if you get 0 over 0, or if you get infinity over infinity, now we have another tool. We can do L'Hopital's rule. But we can still factor. We can still factor, and we can still do all the things we did before. So L'Hopital's rule hasn't really changed anything from what we knew before that we could do. It's just added one more thing. If you get 0 over 0, infinity over infinity, you can do L'Hopital's. Multiples of 4, yeah, as it says M4. Yeah, M4 means multiples of 4 on the assignment sheet. Now, to be honest, if I'm working on those, what you might do is save some of those, like probably what I'll do. So like 56 through 80 is that where it says multiples of 4. But to be honest, you should be able to do all of 55 through 80, right? You should be able to do all of those. So to be honest, that's kind of the homework for tomorrow. And then tomorrow I'll probably say, and I'm going to give you kind of a review worksheet with some problems. But also I would say go and do whatever ones you haven't done on that page, just as for more practice, right? Because you never know. I got to come up with problems on the quiz from somewhere. I might have pulled them out of there, right? So it's not a bad idea to review through those. So if you're looking for, so for you, probably got time to work on class. Right. I know. I just thought I'd give you, but you don't have to start on that. I think we'll have quite a bit of work time to work probably, so you'll be able to work on class. Unless you're so prepared after we talk about stuff, you want to do the quiz, last part of class, maybe start it to see. Well, if we start it, we got to finish it. That's the thing. So.